All right, let's dive right into this explainer. Behind this seemingly chaotic world around us, there actually lies a strict, totally invisible set of rules. Today, we're going way beyond the basics to decode the atomic foundations of matter. We're exploring not just what stuff is made of, but the brilliant mathematical logic that dictates exactly how it all connects. But first, we're starting with a classic mystery. Picture this. You're doing that simple science experiment where you pour baking soda into a flask of vinegar. You get that brisk effervescence, right? A whole lot of bubbling and fizzing as carbon dioxide gas escapes. Now, if you actually weigh the flask before and after this reaction, you'll notice the final weight is less. So where does the weight go? Does mass just disappear into thin air? Is matter actually destroyed? Just keep that in the back of your mind as we go. To solve this mystery, we're going to flip through the cosmic rulebook of chemistry. We'll hit 5 key areas: the laws of matter, Dalton's atomic theory, how atoms combine, writing chemical formulae, and finally, measuring molecules. Let's get into it.
Starting with Section 1, the laws of matter. This is where we establish the absolute, unbending rules of the universe.
Okay, let's answer our baking soda mystery. If you do that exact same vinegar and baking soda experiment, but this time you stretch a balloon over the mouth of the flask to trap that escaping gas, something amazing happens. The mass on your digital scale remains exactly the same before and after the reaction. This perfectly proves the law of conservation of mass, proposed by Antoine Lavoisier way back in 1789. It tells us matter can neither be created nor destroyed in a chemical reaction. The gas didn't just vanish, it just changed form and floated away because we didn't catch it. And this balloon experiment literally perfectly illustrates this whole point. As Lavoisier put it, in every operation, an equal quantity of matter exists both before and after the operation. Chemistry is just a perfect balancing act. Nothing is ever truly lost, and honestly, nothing is magically created from thin air either. The atoms, they're simply rearranging themselves into new formations.
Right on the heels of Lavoisier, another scientist, Joseph Proust, figured out our second vital rule, the law of constant proportions. He discovered that compounds aren't just random, chaotic mixtures. They always team up in strict, totally predictable proportions by mass, no matter how the compound is formed or where you find it.
So what does that actually mean for us? Well, think about pure water. It will always break down into exactly 1 part hydrogen to 8 parts oxygen by mass. Always. It doesn't matter if you scoop that water from a rushing river, pump it from a deep bore well, or take it straight from the ocean. If you purify it and break down 9 grams of that water, you will always get exactly 1 gram of hydrogen and 8 grams of oxygen. That 1:8 ratio, completely non-negotiable.
Moving to Section 2, Dalton's atomic theory. Knowing these rigid rules, let's meet the microscopic players who actually follow them.
Enter John Dalton in 1808. He took these laws and synthesized them into one brilliant, unifying theory. He basically said, okay, all matter must be built from indestructible little puzzle pieces called atoms. He proposed these atoms are indivisible. You can't break them down any further in a chemical reaction. Atoms of the same element are identical in their mass and properties, while atoms of different elements are, well, completely different. And crucially, to explain Proust's law, Dalton realized these atoms have to combine in simple whole numbers. I mean, you can't have half an oxygen atom, right?
Which brings us to Section 3, how atoms combine. So how do these individual puzzle pieces actually stick together to build our world?
Atoms are kind of like characters, driven by a single motivation. They just want to be stable, and they do that by getting a full outer shell of electrons. They generally use 2 main strategies here. Some atoms prefer to peacefully share their valence electrons with a neighbor, creating a covalent bond. Think of 2 hydrogen atoms happily sharing their single electrons to form a stable molecule. But then you have atoms that do a complete transfer of electrons, forming an ionic bond. One atom gives up an electron and becomes positively charged, while the other takes it and becomes negatively charged. Because opposites attract, bam, they lock together like magnets.
Now, why should we care about this microscopic behavior? Because it dictates literally everything we see. Look at this comparison. Ionic compounds are locked together by strong forces, so they have super high melting points and usually dissolve easily in water. Most importantly, when salt dissolves, its charged ions can move freely, meaning it conducts electricity. Covalent compounds like sugar are the opposite. Lower melting points, often don't dissolve easily, and because they don't form ions, no electricity flows. The invisible bond completely changes the visible, real-world behavior.
Okay, Section 4, writing chemical formulas. Let's decode the actual language of chemistry.
Writing formulas might look super intimidating, but there's a fantastic little trick for it called the crisscross method. It's 3 incredibly easy steps, so you don't have to memorize a giant textbook of formulas. Step 1, just write the symbols of the elements. Step 2, write their valencies. That's their combining power or charge right underneath. Step 3, you literally just crisscross the numbers, moving them to become the subscript of the opposite element.
Let's test it out on something familiar, water. We write down H for hydrogen, O for oxygen. Hydrogen has a valency of 1. Oxygen has a valency of 2. Crisscross those values. The 2 drops down to the hydrogen, the 1 drops to the oxygen. And perfectly, we get H2O. This simple little crisscross ensures the atoms are balanced electrically, forming a perfectly stable compound.
Finally, Section 5, Measuring Molecules. Let's talk about keeping score with mass. Calculating mass is actually super straightforward. For covalent compounds, those distinct little molecules, you just add up the atomic mass of all the atoms in your formula. Taking water again, H2O. Hydrogen has an atomic mass of 1 atomic mass unit, or U, and we've got 2 of them, so that's 2. Oxygen has an atomic mass of 16 U. 2 plus 16, boom! The molecular mass of water is precisely 18 atomic mass units. It really is that simple.
But wait, what about those ionic compounds? Remember, they don't form independent little molecules. They build massive, repeating 3D crystal structures. So instead of molecular mass, we calculate the formula unit mass. We do this by taking the simplest ratio of its ions, that formula we just learned how to write, and adding those masses up. Like, take a complex crystal like calcium nitrate. We grab its formula, CaNO32, and just add the mass of 1 calcium, 2 nitrogens, and 6 oxygens. Mathematically, every single atom in that giant crystal lattice is accounted for. So look, everything we've covered today in this explainer, from Lavoisier's sealed balloons to Dalton's whole numbers, proves that in ordinary chemical reactions, mass is perfectly conserved. It's a rock-solid rule of our universe. But I want to leave you with this provocative thought. Are there any chemical changes that actually break the law of conservation of mass? What happens when we smash atoms apart, leaving basic chemistry behind for the wild realm of nuclear energy? Does the cosmos